So, yesterday we ended with this statement that I have boxed here still. So this is the thing that tells us the form of any Pythagorean triple. So in particular, um, uh, so if I have any primitive Pythagorean triple, then C is odd, exactly one of A or B is even. So assume that B is the even one, then in that case there exists relatively prime M and N, such that A is the difference of squares of those two N and M, so N squared minus M squared. B is 2 times Mn, and C is the sum of the squares M and N. So anyway, and quick example was if N was 2 and M was 1, we get the most famous Pythagorean triple 3, 4, 5. So I'm not going to go through this entire proof. So the proof is, I believe, where does the proof end? Proof ends on page 88, begins on page 85. So the proof here is, it's not as long as it seems. It does require two lemmas that I'm going to state, but apart from that, I'm not going to give the details for the rest of the argument. So if you like, you can have a look at that. So requires two lemmas. And I'll state those now. So one, so first lemma required in this proof is the following. So let k be greater than or equal to 2, and let A, B, C be relatively prime positive integers. Okay, such that A, B, so A times B is a power of k. It's n to the k for some integer n. Okay. Then A and B are each kth powers of integers. Okay. So A and B are relatively prime positive integers. K is greater than or equal to 2. If A times B is n to the k for some integer n, then A and B are each kth powers of integers. Okay. You can prove this via the prime factorization. So use prime factorization of n to see why this works out. It's just a bit of bookkeeping. I'm not going to go into the proof of this either. Because if I went into the proof of both, the lemma is actually doing the proof of the theorem itself wouldn't take too much longer. So there's one more lemma that this requires. I'll have to put it on another sheet. Actually, no, I don't. I can put it right here. I can fit it right here. Here's the other lemma that this proof requires. The square of an odd number is one more than a multiple of 8. The square of an even number is a multiple of 4. Okay. This is not going to take you too much work to think about. In fact, just using the definition of even and odd gets you there. There's not a whole lot needs to be said here, but these two limits combined do a decent bit of the work in this theorem. The rest is a bit of careful bookkeeping. So anyway, so this theorem is nice, but the method that is proved outlined here in the book is not really geometric at all, and there is a very nice geometric approach to this that I'm not going to go through entirely right now. I'll do it later because at the very end of the course, my plan is by the end of the course that I am able to spend at least 3 full lectures on elliptic curves, and when we talk about elliptic curves and what elliptic curves mean for number theory, I will finish this example because it's kind of the first meaty example of what's really going on here. So right now I'm just going to start it. Okay. So of course, the thing to note, right? So this tells us how to generate the Pythagorean triples, right? And any primitive Pythagorean triples of that form. So it's telling us that any solution of any primitive solution, which just means GCD 1, to this Diophantine equation, x squared plus y squared is equal to z squared. Finding these this particular form of solutions for these things it was completely solved by this theorem, right? It says that any of those particular kind of solutions were of that form enumerated by the theorem. So then what does this have to do with elliptic curves? Well, the idea is say I have a triple like this, or to move it into the usual notation here, I have a solution. A squared plus b squared is equal to c. So I know that there's infinitely many solutions. Let's say I have a solution like this. Well, having a triple ABC satisfying this, if I divide both sides by c squared, what do I get here, right? I get a squared over c squared plus b squared over c squared is equal to 1. Or rewriting this, I get a over c squared plus b over c squared is equal to 1. Now I've moved out of the realms of, so I've moved entirely out of the realm of a Pythagorean triple, because now I've divided through by c. There's no guarantee. In fact, if this is a primitive, triple, then this will be guaranteed, in fact, to not be an integer, right? So a over c and b over c will not be an integer in this case. Those will be rational numbers. And so, well, if I have this equation satisfied, then what I'm saying is that through multiplying both sides by c squared, I have the typical Pythagorean identity. But of course, immediately when you see this, what do I have here? This implies that the pair AC BC lies on unit circle. Okay. Well, I drew the arrow going in both directions right now, and I did the backwards direction in words. But to actually write it out, right? Let D. So if so, this lies on a unit circle. Unit circle is x squared plus y squared is equal to 1. Well, suppose x and y are two rational numbers such that x squared plus y squared is equal to 1. If D is any common denominator of x and y, then what can I do? I can multiply both sides by d squared if you like, right? If it's a common denominator of x and y, then xd and yd are integers, and xd squared plus yd squared is equal to x squared d squared plus y squared d squared. I can factor out the d squared, and that's just multiplied by 1, so this is equal to d squared, i.e. xd, yd, and d is a Pythagorean triple. Okay. So, if I begin with a Pythagorean triple, I end with the fact that Pythagorean triple ABC yields me a rational, so these are both AC, BC are rational numbers. Again, this is a primitive triple. These are actually guaranteed to not be integers, right? So they're guaranteed to be rational but not integers. Yeah, right, exactly. So the statement was A over C and B over C are guaranteed to be in lowest terms if the triple's primitive. That's right. And the thing is that they're, it's again because of that, these essentially what I'm saying here is that I really get some I really get some rational point here on this curve. And the curve in question, of course, is unit circle. So rational point on unit circle. Sorry, I've used. Corresponds to primitive Pythagorean triple, and vice versa, right? If I start out with some rational point on unit circle here with coordinates x, y, satisfying x squared plus y squared is equal to 1, take any common denominator, and you see that xd, yd, d is Pythagorean triple. So main thing is so rational points, i.e. points on unit circle with rational coordinates, on unit circle correspond to Pythagorean triples. So there is a geometric way, of course, to find these things that I'm not going to get into right now because the methods I use are like the first example of methods that we'll use to deal with finding rational points on elliptic curves. So this is a really the general that general problem I just said, finding rational points on elliptic curves. That's an insanely complicated problem that I'm sweeping under the rug right now. But we'll get to very simple examples of that later. That's kind of where I want to end the course. So that discussion's on page 89, and like I said, we'll get back to that before the end of the course. So maybe like 3-ish days out from the end of the course. I'll return exactly to this example to show how you can get the exact same formula that we got in the theorem, which told us what any primitive Pythagorean triple had to look like. We can get exactly, we can reproduce exactly this formula using geometric methods that deal with this correspondence, okay, between Pythagorean triples and rational points on unit circle. Okay. So that's kind of one of the best early examples of this. In fact, if you look at most textbooks on the subject, this is almost always the first example that pops up. Okay, so I'm going to, as I mentioned yesterday, going to skip 5.5 and 5.6. So skipping 5.5. So 5.5 is both of these are like one-page chapters. You can have a read of them if you like. It won't take that long. There's not too much info there. It's just some particular applications of prime factorization. So 5.5 is difference of squares. 5.6 is prime factorization of factorials. So this is a difference of squares. Again, it has like one theorem in it. 5.6 is prime factorization of factorials. Okay. So we'll be skipping these. Like I said, you can have a read of them if you like. So we're skipping these so that we can spend more time on 5.7, which is the Riemann Zeta function. Okay. So cool thing is by the time we're done with this discussion, we'll be able to state and talk about the Riemann hypothesis, which is almost certainly the most popular open question in all of math. And in addition, I'll be able to relate this not only to statements that we've already shown about primes, that's the first thing I'll do, but also I'll be able to relate it to statements relating to the twin prime conjecture, which is something I mentioned earlier in the course. So what's the Riemann zeta function? So let's say let S be greater than 1 be a real number. Well, if I start out with a real number, maybe I'll write it first before I say what I want to say. So the Riemann zeta function is defined as the following. So this is testing my ability to write zeta. Zeta is, I think zeta is trickier to write than Cassie. And for some reason I'm better at writing zeta on a board than on paper. But so it's zeta of s is the sum from n equals 1 to infinity of 1 over n to the s. Okay. All right. So, a couple of things to note here. So note, you might notice that there's a reason why we wanted s to be greater than 1. If s is greater than 1, that the series in question converges. This is one of the first things that you're asked to show about series, right? So here you can use the integral test to do this if you like. When s is equal to 1, you know that the series involved is the harmonic series, which diverges. But if s is bigger than 1 here, you know, this was, you called it a p series in like Calc 2. And the integral test was the thing that you used to show this directly. So this series converges if s is bigger than 1, and I don't have to worry about anything. The other thing that I wanted to note is that I've defined the Riemann zeta function for a real number. It turns out that I can extend this to be defined not just for real numbers, but for complex numbers. So if you know anything about complex analysis, this is called the analytic continuation. This can be analytically continued to be defined for complex numbers just as well. But for all of my purposes I'm going to talk about in this section, I'm just going to say that s is a real number. Okay. But like I said, I can actually, using complex analysis, I can extend this. So the actual Riemann zeta function that you will come across if you read in the literature, this will be defined for s a complex number, not just a real number. Okay. All right. So for hundreds of years, it's been known that there is a relationship between this zeta function and the prime numbers. Okay. Of course, there's a lot of specifics to that statement. And as we'll see, there's a relationship between where this thing is equal to 0, and we'll talk about that later, and how the primes are distributed. Okay, so there's also the specific question of distribution of the primes, right? How the primes are spaced out among the integers and the zeros of this thing, if you like. So I'm going to I will talk about that stuff later, because that doesn't come until we've talked about extending this to include complex numbers s. The idea here is that there's an immediate relationship between this thing and the primes in the following form. So this is the main theorem that we'll talk about to drive this point home. So let s be greater than 1, then zeta of s can be written, or can be expressed as the product over primes p of 1 minus p to the minus s to the minus 1. Okay. Written, another way, if you don't like writing these with negative exponents, you want to see this in another form. This equality is not saying anything other than like algebra 1 stuff. So this is, maybe I should, it's whatever you prefer, whether you prefer written like this or like this. But I think it looks more confusing written in both of these ways. Maybe this is okay. I think it looks more confusing written like this. But anyway, so this is the main way that I'll think about expressing this. Oh, I'm off camera. There we go. Okay. Where this product's over all the primes. Okay, so where product is over all prime numbers. Okay. Okay. So, how do I show this? If you are familiar with the sort of minor hand waving that has to be done when, say, you're looking at the classical proof that Euler did for the Basal problem, which I'll also talk about in a second. Then you'll be familiar with what I'm going to do in this proof, which is I'm going to ignore any hang-ups that come from the specifics of convergence, and I'm going to do all these operations kind of without worrying too much about it. The point is that it does work. I don't actually have to worry too much about convergence, and the manipulations that I'm doing do work, even though to be 100% thorough, I would need to say more to justify. But that would require me dipping more into analysis that I want to do right now. So maybe I'll start fresh on a new page rather than crowd this one. So this is what we want to show. We want to show that, in fact, another way of expressing this sum is as this product over all the primes of this weird expression here. Okay. So how does this work? Well, by the formula for computing geometric series, and as I always tell my Calc 2 students, right, when you're trying to compute with a series, then it's either geometric or telescoping. If it's not one of those things, then essentially you have no idea what to do. It's more or less impossible to compute with a series otherwise. So what's the formula for geometric series tell me? It tells me if I have this geometric expression that is the same, so long as this thing converges, which it does when absolute value of r is strictly less than 1. This is 1 over 1 minus r, or rewritten using the notation I'm going to be using, 1 minus r to the minus 1, whenever absolute value of r is less than 1. Okay, there's a number of ways, of course, that you would need to show this, right? It diverges otherwise. And you can show that through convergence tests, or you can just take that as a fact from classifying geometric series. Let r equal p to the minus s. Well, if s is bigger than 1, then we're in good shape, right? So if s is bigger than 1, if s is bigger than 1, then r, defined in this way, is strictly less than 1. So what do I get? I get that 1 plus 1 p to the s plus 1 over p to the 2s plus 1 over p to the 3s, and so on. Well, I'm not going to write another term here. I don't know why I did that. So this is 1 minus p to the minus s to the minus 1. Okay. Okay, so I have this expression that is showing up on my right-hand side here, under the product, right? Obviously, I would need to do the product over all primes there, but I have this thing showing up in the product here expressed in terms of a geometric series, and maybe it's not immediately clear how this is going to work out. So in order to see where I'm going to end up with this, I want to first see how this works when I do the product of two things of this form, right? So consider the product 1 minus 2 to the minus s to the minus 1 times 1 minus 3 to the minus s to the minus 1. Okay. Okay, so let's see how this works out. So here's where our Basal problem trickery comes in. If you don't know what the Basal problem is, I'll remind you here in a little bit. So then I have a product of two series coming from this thing. So I have 1 plus 1 over 2 to the s plus 1 over 4 to the s plus 1 over 2 cubed to the s, so that's 1 over 8 to the s, and so on. Okay, that's what I get from this term. And then I'm multiplying that by 1 plus 1 over 3 to the s plus 1 over 9 to the s, and so on. All right, that's the 3 squared to the s term. Okay, so I have the product of these two things. Okay. So then how does this work out? Well, let's expand this, right? And let's be clear with the notation so that we're not missing anything, and we try to list out all types of things showing up in this expression, right? So I want to list all types of terms that are going to show up. So first, I just expanding this, right? I have this entire series times 1. Okay, and again, you know, this is, you might be like, oh, how can you do this expansion, right? So it turns out all these manipulations work out fine, and of course, you know, at the time of Euler, these things were kind of done willy-nilly, and no one batted an eye. But of course, in certain instances, these have to be justified. I mean, this would have to be justified anyway, but the point is that in certain instances, these types of operations and manipulations involving series can fail. But it turns out that in this case, they don't. But I'm not going to spend any more time justifying them. So we can just do the intuitive thing here for these series. I'm going to take this whole series and multiply it by 1, so I get everything that looks like a term there. So 1 plus 1 over 2 to the s plus 1 over 4 to the s plus 1 over 8 to the s, and so on. I get that whole series, right? And then in addition to terms that look like that, I get the next thing, right? I take this whole series and multiply by 1 over 3 to the s, so I have plus 1 over 3 to the s plus 1 over 2 to the s times 3 to the s plus 1 over 4 to the s times 3 to the s, and so on. And I get infinitely many terms that progress in that fashion. And then I get the same thing for the next bunch of terms. I get this whole series multiplied by 1 over 9 to the s, right? So I get plus 1 over 9 to the s plus 1 over 2 to the s, 9 to the s, plus 1 over 4 to the s, 9 to the s, and so on. Okay. But then rearranging these, right? Rearranging these again. Let's ignore any issues with rearrangement that I'm doing here that might pop up. There's no issues that come from rearranging these terms like this. What would I get? So I want to make sure that these denominators are in increasing order like this. So I do 1 plus 1 over 2 to the s. I have a 1 over 3 to the s here, so this is 1 plus, or plus 1 over 3 to the s. Next, I have a 1 over 4 to the s. I don't have a 5 showing up anywhere. The next thing I get is a 2 to the s times 3 to the s, which is actually 6 to the s, right? Plus 1 over 6 to the s. I don't have a 7 here, but I do have a 1 over 8 to the s showing up. Where is my 4 times 1 over 2? Oh, yeah, here it is. Here's my 1 over 8 to the s. So it's 1 over 8 to the s, plus I have 1 over 9 to the s. Plus, here I have a 4 to the s times 3 to the s, so that's a 12, 1 over 12 to the s, and so on. What is it that's going on here? What is happening here? That's one of the reasons. The terms being positive is one of the reasons, Robert. So the question in chat was, does it work out fine because all the terms are positive? When you're doing manipulations like this, so let's see, what's the bare minimum I need to make sure that all of the manipulations I need to do here work out? I'm not sure exactly what the minimum possible. I'd have to think about it for a second. To think what the minimum possible assumption I would need on all of this stuff to make sure that everything works out, all this rearrangement works out. I'll think about it and might add it in. I'll probably edit it to the description. Oh, another thing that reminds me of of something. I've noticed that a couple of people had emailed me and asking where the lecture videos were. And normally, when I live stream the lectures are up. I mean, in the past anyway, I hadn't been paying attention for this course because I thought that this was how it always was. Normally, when I live stream a lecture, it is posted to YouTube automatically and I mean, it normally takes like maybe 3 to 5 hours at most. The problem is for whatever reason, the last couple of lectures that I've been paying attention to haven't been uploaded for it has taken YouTube like 20 hours to upload the video. So they essentially don't even get uploaded to the next day. So I don't know what the deal is with that. I'm going to try to see if there's anything I can do on my end to fix that. If it's purely on YouTube's end, then there's nothing really I can do. But if there's something I can do on my end, I'll try to fix that so that they're uploaded only a couple hours after the stream. So I'm going to see how long it takes YouTube to upload this one, for instance. But anyway, okay. So after this quick rearrangement, then what do you notice, right? What is it that's going on in these denominators? So these are numbers showing up here, raised to the s in the denominator. And what do you notice about these numbers? Every single number only involves in its prime factorization the primes 2 and 3. Right? I'm going to get infinitely many terms, but the terms in question only are the numbers that involve nothing but 2's and 3's in its prime factorization. And if you think for a second, I'm going to get every such number. I'm going to get every number that involves only 2's and only 3's in its combinations of 2's and 3's, I mean. So only 2's and 3's in its prime factorization. I'm going to get every single number like that, but I'm not going to get any numbers, say, that also have a 5, right? So for instance, we didn't get a 1 over 5 to the s. I don't have a 1 over 10 to the s showing up here, or 1 over 15 to the s, right? I have none of those. Okay, and so a way to actually write this out is that this is the sum, okay, over in the set S 2, 3. That is exactly what you think it is, but I'll write it out here in a second, of 1 over n to the s. Okay, where S of 2, 3 is the set of integers whose prime factorizations only involve powers of 2 and 3. Okay. All right. Now, a couple things that I need to say here, right? You can probably already see where this is going, that as I multiply more and more terms here, what I'm doing is I'm essentially adding in primes into this set. So when I look at, say, the product, which is this times 1 minus 5 to the minus s to the minus 1, what I get then is that can be expressed as this sum over n in s of 2, 3, 5, right? But before and of course this is going to lead me via prime factorization to what I want. Now, there's a slight thing that I have to worry about, and it might also be something that you've thought about. When you're trying to do this organization here, or when you're multiplying by more terms, the thing, of course, you have to be careful with is, yes, I have done this slick rearranging here in this order, but I have to make sure that the way that this works out is in such a way that I don't get repetition so that I'm double counting, right? So what I mean by that is when I have this 1 over 4 to the s showing up here, I want to make sure there's not another copy of 1 over 4 to the s that I haven't accounted for, so that actually I get, this is plus 1 over 4 to the s plus 1 over 4 to the s, so I get plus 2 over 4 to the s, right? I get 2 of those terms, just for example. I want to make sure something like that doesn't happen. So why does something like that not happen? This is by uniqueness, okay, of the prime factorization. So uniqueness is what tells you this only happens once. So note, this is a big note here. So my proof is being continued from the previous page. So note each integer in S of 2, 3 occurs exactly once. Once in the sum. Okay. All right, so example, right? 12 is in S of 2, 3. Okay. And the corresponding term in the sum is 1 over 12 to the s, which comes from a single place in the sum. It comes from a multiplication that is 1 over 4 to the s times 1 over 3 to the s. All right, so going back really quickly, it comes from, this term here comes from exactly one place, 1 over 4 to the s times 1 over 3 to the s here. All right, this is the only combination that does it. Okay. All right. So it's the uniqueness of the prime factorization. Guarantees that I only get one such copy. Okay. And since this is supposed to be rounding out our chapter on applications of prime factorization, this is key. Okay, and this is a nice fact. Okay. All right. Note also, 1 is in S of 2, 3, since trivially 1 is 2 to the 0 times 3 to the 0. So when I say powers of the primes 2 and 3, that's fine. Okay, so we know that 1 is also included. This makes our notation slick. Okay. And here's further notation. S of, say, P, Q, and so on. P, Q, we usually use these for primes. I'm just going to say R here and so on. This is the set of integers whose prime factorization only involves primes P, Q, R, and so on, right, in the same fashion. Okay. So then using this notation, if I were to tack on one more to this product, 1 minus 2 to the minus s to the minus 1 times 1 minus 3 to the minus s minus 1 times 1 minus 5 to the minus s minus 1. If I tack on and recombine, how's that going to change? Going back, how is that going to change what I have here? Well, in this product, I'm going to tack on another series that's going to involve, it's going to be 1 plus 1 over 5 to the s plus 1 over 10 to the s and so on. So then, 1 over 5 to the s, 1 over 25 to the s, and so on. And then, yes, I am going to get a 1 over 10 to the s from 1 over 2 to the s times 1 over 5 to the s. And so what I'm going to get here is just inserted in this rearrangement. I'm going to get 1 over 5 to the s, so 1 over 10 to the s. Again, that comes from 1 over 2 to the s times 1 over 5 to the s. 1 over 15 to the s, and so on. So I'm going to get the multiples of 5 here, and that's going to fill this in. So doing that, then, the fact that I say that it fills it in, what do I get? I get the sum over n that are in the set of integers whose prime factorizations involve 2, 3, and 5, 1 over n to the s. Okay. So then in general, if P sub m is the mth prime, then the product of these things up to the mth prime yields this sum over integers involving, or with prime factorizations involving all primes up to the mth prime, 1 over n to the s. Okay. So then let m go to infinity, then the left-hand side converges to just symbolically what we mean by the symbol. I get this product over all primes, right? If m's going to infinity, then I'm just listing out all the primes here of 1 minus p to the minus s to the minus 1. And this thing on the right becomes the sum over integers whose prime factorizations involve all the primes. Well, which integers are those? Well, it's all of them from 1 to infinity. But that's the zeta function. Okay. So why are we done here? A couple of things. Not only did we use uniqueness of prime factorization to only get me one copy here, we also used the existence portion of prime factorization here, because the fact that this thing on the right, as m goes to infinity, converges to be exactly this expression is the statement that when you say you're going to be summing over all integers n whose prime factorizations involve all the primes, well, by existence, right, by the existence portion of prime factorization, that's all the integers, right? That's the statement that every integer can be written as a prime factorized thing, right? It's a product of a bunch of primes, possibly with a repetition. So that's all the integers. Okay. So that is a really nice fact. Let me put the fact back on the screen since it took us a couple of pages to prove this. So here's the fact that I'm showing. This connection between the zeta function defined in this way, where notice that there is absolutely no reference to prime numbers here in the definition of the zeta function at all, and yet immediately, with stuff, I mean, you could have, knowing prime factorization, you could have done this in Calc 2. I mean, obviously this would be a harder Calc 2 thing, but as far as what we used here, we didn't use anything outside of Calc 2 other than knowing about prime factorization. Here is what I have, this nice expression. So first application of this nice expression is another proof that there's infinitely many primes. So of course you've already seen one proof, but here's another. So proof, I'm doing this a lot often, so state fact and then I'll give proof. There are infinitely many primes. Okay. There are infinitely many primes. So this proof is due to Euler. Okay, he is the one who discovered this particular proof of this fact. Okay, so what is the idea? Study what happens to zeta of s as s approaches 1 from the right. Okay. Remember, for zeta of s to even be defined, s has to be greater than 1, so I'm approaching 1 from the right, from through values greater than 1 here. Okay. All right. So we need a lemma first. We need a lemma to proceed. So the lemma in question is the following. So if s is greater than 1, then zeta of s is greater than or equal to 1 over s minus 1. Okay. So here's the proof. This is one of these analysis style proofs that's really a simple application of an obvious inequality and then applied in a way that is tricky. So this is a common technique. It's going to be used by me at least twice more throughout proofs involving the zeta function. So let n be greater than or equal to 1. If n is less than or equal to some x, then since s is greater than 1, 1 over n to the s is greater than or equal to 1 over x to the s, right? So n is some fixed thing greater than or equal to 1. I don't know what x is. I'm just saying that n is less than or equal to x. Now, if n is less than or equal to x, then the fact that s is greater than 1, n is greater than or equal to 1, I have this inequality. Okay. Thus, 1 over n to the s. There is a tricky way that I can write this. Okay, you may be familiar with this from analysis because this is a very much an analysis trick. But it's when I know that the thing that I want to be talking about involves integrals, then I can use, of course, like one of the most important facts about integrals is that integrals preserve inequalities, right? So if you have an inequality on the integrand, the thing that's going underneath an integral, then you get, that the integral preserves that inequality. And so knowing that, I also know that there is a very particular way I can set up integrals so that, for instance, I can express this as an integral that is a trivial integral that allows me to see how I can apply this inequality. So the way that this goes is the following. I rewrite this as an integral. The integral I rewrite it as is the integral from, and because it might not be clear, I'm integrating with respect to x here, so this is the integral from n to n plus 1 of 1 over n to the s dx. So think about this for a second. This is an integral, okay, that is an integral over an interval of length 1 of a constant with respect to x, right? 1 over n to the s. S is some fixed number greater than 1. N is fixed greater than or equal to 1. So this is a constant with respect to x, and so this is just the integral of, I could pull this out if I like. So this is 1 over n to the s times the integral from n to n plus 1, that's over an interval of length 1, of 1 dx. So this is, I've done nothing here, right? This is a trivial fact. Okay, but why did I write it in this form? Why did I want it written in this form? I wanted it written in this form so that I can compare it to this thing, the integral from n to n plus 1 of 1 over x to the s dx. Okay, and because of this inequality and integrals preserving inequalities, this is what I get, right? And this is not a trivial integral, right? This is an integral of 1 over x to the s dx over this interval of length 1. So this is not trivial. Then it's going to fall out of this fact, what I want to say. So zeta of s, if I actually write out what that is, that's 1 plus 1 over 2 to the s plus 1 over 3 to the s, and so on. Its nth term is 1 over n to the s, and so on. Okay, that's what it looks like. Well, then what can I do? I can actually replace each of these terms, if I like, with the corresponding integral here, right? So using this, especially this bit here, I can, well, I need to use this fact too, sorry. I can replace each one of these terms with this integral so long as I slap a greater than or equal to sign on it. Okay, so this is greater than or equal to the integral from 1 to 1 plus 1, so 1 to 2 of 1 over x to the s dx, plus here's the integral from 2 to 3 of 1 over x to the s dx, and so on all the way out to the nth term, which is the integral from n to n plus 1 of 1 over x to the s dx, and so on all the way. But what is this? This right-hand side here is actually just the indefinite integral, the integral from 1 to infinity of 1 over x to the s dx, right? But I can evaluate this, right? Remember how to deal with improper integrals. So this is x to the 1 minus s over 1 minus s. And this is evaluated from x equals 1 to infinity, which leaves me with here, since s is bigger than 1. Oh, I'm off screen. Okay. Since s is bigger than 1, evaluating at infinity, I get 0 here, right? So remember, another way is, you know what this thing is. When s is bigger than 1, this is a convergent improper integral. When s is less than 1, it is divergent, right? This is actually infinity. Here, this thing is this thing's convergent, though, because in this exponent here, this is going to be a negative thing. So this is going to be 0 minus 1 over 1 minus s. So that's 1 over s minus 1. So what I've said is that zeta of s is greater than or equal to 1 over s minus 1. Why do I need this lemma? Okay, this lemma is actually the main part of Euler's proof. So if you started with this lemma outside the proof, this proof would be much shorter than it appears. So you might be thinking right now, wait, like, it might be interesting to see something proved in another way, but like this is way longer than the other method of doing it. But it's actually not so bad. Okay, so to see that it's actually not so bad, imagine that I had proven this lemma as a general fact, right, about the zeta function already. Then this proof is a lot quicker. Now I know that that's kind of cheating, but I mean that's ultimately, if you think about like what does it mean for a proof to be elementary? What does it mean for a proof to be simpler than another proof? Right? You run into this conundrum. So this is kind of a philosophical question, but literally, what does it mean for a proof to be simpler than another proof? If you just say the words, oh, what matters is that the proof is shorter, right? It uses the least amount of English words, okay? Or symbols even, right? You could break it down to characters, right? It is as short in characters as possible. Right, we'll do that so that we include all the math symbols we're using, right? So it is, it's as short as possible in that way. The problem with that is that would encourage basically wrapping everything up in definitions. So any possible situation that could happen in math, you would have a special name for it, right? And then you would just say that thing, right? So you would say this fact follows because this thing is like 5 die connected or something, right? That's what you would say. You would say some stupid term that you've invented that actually incorporates like 10 theorems in it, right? Rather than actually stating all those theorems out. So is that really a simpler proof? Well, not really, right? That's you've just wrapped up like 50 theorems into a single term, to describe that configuration. So it's not really a simpler proof. So if we start talking about which proof is simpler, we kind of get into silly problems along those lines. Okay, but why does this lemma basically do it? So proof continued. The lemma basically finishes the proof. Okay. So recall, lemma says that zeta of s for any s bigger than 1, which is exactly all the s for which zeta is defined, zeta of s is greater than or equal to 1 over s minus 1. Okay, that's what my lemma says. Okay, since 1 over s minus 1 goes to infinity as s goes to 1 from the right, the lemma says that zeta of s must go to infinity as s goes to 1 from the right. Because zeta of s is an upper bound for 1 over s minus 1. So if 1 over s minus 1 is going off to infinity as s goes to 1 from the right, then zeta of s has to go to infinity as s approaches 1 from the right. Okay. All right. So then suppose that there are finitely many primes. Okay. Then zeta of s equals the product over all the primes of 1 minus p to the minus s minus 1, where the product is over finitely many primes, i.e. it's a finite product. It's stated a little confusingly. I mean, if there's finitely many primes, then the product being over all primes is only over finitely many. I'm not saying that I'm stopping short. I'm still hitting all the primes. It's just that I've said there's finitely many primes. So the product on the right's a finite product, right? So it's a finite product. Each factor in the product is continuous. Okay, so each factor in the product is continuous at s equals 1. Thus, the limit as s approaches 1 from the right of the sum from n equals 1 to infinity of 1 over n to the s, this must be, that's the limit of my zeta function. This must be the limit as s approaches 1 from the right of the product over finitely many primes now of 1 minus p to the minus s minus 1. But I can move this limit inside the product, and because this is continuous and this is a finite product, I don't have to worry about any problems involved with moving this inside here. This is actually just the product over some finite number of primes of 1 minus p to the minus 1 to the minus 1. That's a finite product. This thing, there's absolutely nothing infinite about this. This thing is finite. But this is a contradiction. This contradicts what we just said. Namely, that the limit as s approaches 1 from the right of the sum from n equals 1 to infinity of 1 over n to the s, that's the limit as s approaches 1 from the right of the zeta function of s, but that's infinity. So this is a contradiction. So there must be finitely many primes, or there must be infinitely many primes. Okay. Okay. So the thing is, you might say, why did you have to, if like looking at this last line, you might say, wait, I didn't need the lemma at all, because this would already be a contradiction, because I'm pretty sure this thing is infinite, right? You have to be careful here, though. So I think this is noticed. Yeah, it's at the bottom of where this proof happens in the textbook. There's a slight issue moving limits inside infinite sums. That's a little iffy. So there's some additional reasoning that you would have to use in order to actually move this limit inside the sum and say that this limit is equal to the limit of this sum. Of the sum of the limits here when this is an infinite sum. Moving this inside and saying that this is somehow equal to the sum from n equals 1 to infinity of just 1 over n, that requires a little bit of justification. I didn't want to get into that at all. But yes, you could do it without the limit technically, but it's better to do it with this lemma. And also it proves something about the Riemann zeta function that we didn't know before. Okay, so then finishing up today and then starting tomorrow, we're going to talk about, so the rest of the discussion of the zeta function is going to be really fun stuff, because and it's going to be really fun stuff because this is going to get us into the stuff that's still unknown, even though it's very simple to state now that you have seen the zeta function and a bit about it. So you might already know some stuff. Here's some facts. What is, like, we have a function, we want to know some stuff about it, so then it's nice to know what are some values here, right? So what is zeta of 2? Okay, well, zeta of 2 is, let's just write out the definition. Zeta of 2 is the sum from n equals 1 to infinity of 1 over n squared. So we know this sum converges, but this is not geometric, it's not telescoping. So, by my little mini rule, when a series is not geometric or telescoping, being able to compute it in general is almost impossible. Okay, but this is one of the examples where we really abuse the almost here. So this has an answer. If you know the answer, you might type it into chat if you've seen this before. Also, it's no surprise that the guy who first discovered this was Euler, and this was called the Basal Problem. Okay. So this is the Basal Problem. And so Euler showed that this sum is pi squared over 6. Okay. So this is the Basal Problem. If you have never seen a proof of this, I would love to show it. I don't have time to do it now. I almost always do it for my Calc 2 students because all that is needed to do the proof of this really is Taylor series stuff and then just general being familiar with how infinite series work. So you need series. Okay, so to do the proof as Euler did it, all you need are series and Taylor series. Because he was a little hand wavy with some of the manipulations involved, you need a little bit more to justify what it is he's doing. But to see the proof as Euler did it, and it is technically a correct proof because all those manipulations were turned out to be fine. But to see the way that Euler did it, it's actually a really, really clever proof. So if you've never seen that, you definitely should look up how this is done. And there's similar reasoning that works for all of the evens. So zeta of 4 is, of course, the sum from n equals 1 to infinity of 1 over n to the 4th. And it turns out this is pi to the 4th over 90. This can be done in using reasoning that's very similar here. And it turns out if m is an integer greater than or equal to 1, then we know what the even, that's a C. That's not even a zeta. Come on, that's terrible. Okay, so zeta of 2m is this complicated expression. You don't need to remember this off the top of your head or anything. It's minus 1 to the m plus 1 times 2 pi to the 2m times b sub 2m divided by 2 times 2m factorial, where b sub k is the kth Bernoulli number. If you don't know what Bernoulli numbers are, I'll explain here in a second, but Bernoulli numbers were, I believe this is true, Bernoulli numbers were the first, they were the subject of the first ever thing that could be called a computer program. So computing Bernoulli numbers was the subject of the first computing algorithm, basically. What is the kth Bernoulli number? It is the kth, or I should say, it's the coefficient of the kth term. So it's the coefficient of the t to the k over k factorial term in the Taylor series. Maybe I should draw an arrow here. The Taylor series in question is t over e to the t minus 1. This is 1 minus 1 half t plus 1/12 t squared minus 1 over 720 t cubed, or sorry, t to the 4th. You only get the even powers here. Sorry. Plus 1 over the next Bernoulli number is 30,240 times t to the 6th, and so on. So a way of writing this Taylor series then using Bernoulli numbers is the sum from k equals 0 to infinity of Bernoulli number b sub k times t to the k over k factorial. Yeah, that's right. I forgot. So the Bernoulli numbers are taken to be so the Bernoulli numbers are defined in this way, so that you can look at a sequence of the Bernoulli numbers here. But so you see, you start out right here. You get 1, a t power t squared, t to the 4th, and then so these alternate and they're 0. Okay, so they're other than these first three, these alternating ones for t cubed and t to the 5th and so on are 0. The Bernoulli number is 0 for those. Okay. All right, and you can, like I said, you can look at the list of Bernoulli numbers. But anyway, we get this thing that expresses what zeta is for the even numbers. For odds, almost nothing is known. And when I say almost nothing, I mean like almost nothing. So I will start here tomorrow. But here we have a closed form expression for evaluating zeta of an even integer. But zeta of an odd integer, almost nothing is known. And to give you a taste of what I mean by almost nothing, for instance, zeta of 3 was only shown to be irrational like 40 years ago. And in terms of math, 40 years is like yesterday. And I believe that the next one, so zeta 5, 7, 9, 11, it's still not known which of those are irrational. it was only shown 20 years ago that one of them has to be irrational, even though it's thought that all of them are irrational. And I mean, the question is whether or not, so that's just whether or not it's irrational. There's other questions you could ask, whether it's transcendental, things like that. Anyway, I'll start there tomorrow. We'll have a lot of fun discussion of the zeta function. And then after I'm done with that, I'll start on chapter 6 stuff. And then that'll be the very first bit of chapter 6 will be the last stuff we do before your exam over the weekend. So on Friday, after Friday's lecture, I'll post your exam, and you'll work on it over the weekend and turn it in on Monday. So all the material that it will involve will be all the material I get through till through Friday's lecture. All right. So that's the deal. So we'll start there tomorrow, and I will see you all then.